Started. Hey everyone, Manal here. Welcome to our programming podcast. Today, Navya and I are taking you through a full line by line explanation of a C programming topic called Adaptive Traffic Control System and Emergency Vehicle Detection. Next.
The problem statement for our project is a traffic control system that manages vehicles at busy intersections. Emergency vehicles like ambulances and fire trucks are stored in a priority queue to ensure they pass first, while regular vehicles wait in a normal queue. This helps automate traffic management with real-time priority. This system simulates a smart traffic signal that uses data structures like queues for regular vehicles and a priority queue for emergency ones. By automatically detecting emergency vehicles and prioritizing their movement, this system ensures minimal delay for critical services while managing normal traffic efficiently. Let's start decoding from the top. The first three lines are headers, which bring in standard libraries.
Furthermore, the define function, which is set as max 50, sets the queue capacity to 50, the maximum number of vehicles allowed. Furthermore, the two typedef structures, here we define two structures, one for regular vehicles and one for emergency vehicles.
Each has a 2D array to store vehicle names and two integer indexes, front and rear. When front and rear are -1, it means the queue is empty. This function sets both front and rear to -1. It's called during startup to mark the queue as empty.
We call a similar one for the priority queue. Initializing both queues prevents garbage values in memory. The is empty queue returns true when no vehicles are present. That's when front is equal to -1.
This full queue checks if the rear has reached the limit of 49, since counting starts from 0. This prevents overflow. This function enqueues a regular vehicle. First, it checks if the queue is full.
Plus, if the queue was empty, it sets front equal to 0. Then it increments rear and copies the vehicle name into that position using string copy. Finally, it prints a confirmation.
This uses linear queue logic. Once rear hits max -1, no new entries, even if the earlier one's left, because it's not circular.
Now, coming to the passing of the regular vehicle. If empty, it alerts that there's no vehicle, otherwise, the vehicle at front passes the signal.
When the last element leaves, both front and rear reset to -1 to mark empty again. The void in priority queue and void is empty priority queue. These two are identical to the regular queue versions, but for emergency vehicles.
Now, when adding emergency vehicle, it checks fullness, sets front equal to 0 if it's in the first, and stores the name.
Notice the message it acknowledges that an emergency vehicle has a special priority. The void pass emergency vehicle again sets the same logic. DQ from the front and reset indices if it was the last element.
When showing traffic, this function displays the queue side by side, emergency first, then regular.
It loops from front to rear for both queues, printing vehicles' names in order.
This also ensures the user can see which emergencies are still waiting.
The isEmpty queue is like the regular queue, similarly ending with a separator line.
Now, coming to the main function. In main, we declare both queues and variables for user choice and vehicle name. We initialize both queues before entering an infinite loop.
The main menu loop offers add regular, add emergency, let next pass, show traffic, and exit. Let's discuss the limitations. The queue is linear, not circular. So once full, even if the elements are removed, no new elements can join. Input with spaces like fire truck won't work because scanf stops at spaces.
So we can fix that by using fgets or by turning the queue circular with modular arithmetic. Also, to prevent some buffer overflow, we can use scanf up to 19 strings of that vehicle to limit input length. So in summary, the program covers core queue operations, enqueue, dequeue, and display, all in that time complexity.
This is a perfect example of data structures to real-world automation. Possible upgrades include dynamic memory, circular queues, and integration with sensor inputs.
Also now, talking about the output, it's a user-friendly output. So you have to choose your own option. So in the first one, we have chosen the option 1 and entered the byte name. So it just enters into the queue, and we can use any type of choice you want in the further options. And now coming to the plagiarism stuff. So we have used our own handwritten code, and it has come to 14% overall similarity. Thank you.
Thank you.
Hello, this is Molaika.
And this is Aarushi, and today we are here to present our project on plagiarism detection in assignments. So this is a problem statement. We tackle plagiarism where text is rephrased or code is slightly modified. Our solution uses a tree data structure and a tree matching algorithm to detect structural similarities, providing a more accurate score. Why did we use trees? We chose trees to overcome simple word matching limits. Trees map the document hierarchy. This allows us to compare structure, crucial for catching rephrased or modified text. It also gives us more accurate similarity score. So this is our flowchart, and the program has 4 quick steps as shown in the flowchart. Step 1, initialization. We create tree hierarchy, root sentences, and then words. Step 2, data load. We read the text, then pre-process the data for tokenization. Step 3, comparison. We run the sentence level comparison loop to calculate the metrics and combine them for the final score. Step 4, output. We print the final similarity report and plagiarism score. Over to you, Molaika.
Okay, so this is the basic structure, the hierarchical structure of how the assignment would be stored in a tree type of format. So the assignment 1, which is written currently, it is actually the root of the particular tree, and the other texts which are highlighted in dark blue, like this program demonstrates, and the rest of the sentence, it is actually the sentence branch of this particular root, and all the other words written below, those are the child nodes of this particular sentence. Now I'll be showing you all the code. Is this fine?
Yes, it's visible.
Okay, so these are the standard libraries, and this is the specific limit, the content limit, basically the amount of sentences or the amount of words which will be written in a particular assignment. The children limit, especially for the number of words which will be storing in the sentence, and this limit is set just for now. And this is again the max text limit. Now moving ahead, we have the struct tree node. So this is the basic structure of our particular assignment. So our root, it will be having a content part, and it will be having a node type, basically whether it is a sentence or whether it is a word. And then we will be having the another tree node for children. So basically these will be for sentences initially and then for words. Then we'll be having child. So it will basically be representing, in case of root, the child count will be the number of sentences, and in case of sentences, the child count will be the number of words present in that particular sentence. And moving ahead, we have the assignment A text. Currently, we have hard coded these particular strings for simplicity. And moving ahead, this is our assignment structure creation, how we'll be doing that. This is my basic sentence. I'm creating it. Then we'll be again dividing it, extracting words from that particular sentence, and we'll be creating a particular branch, and then we'll be adding those particular words to that particular branch. And then we have the compare function. Now in this particular project, we have kept the comparison quite simple. We have divided it into 2 test cases, and first is wherein all the sentences are same. So simply we are comparing it using the string comparison function, and it'll return us the expected value if the complete sentences are copied. And the second case, I've used a Boolean all words match. So basically, if the particular student has jumbled the sequence of words, but the sentence is same, like the meaning hasn't changed. So in that particular case, again, it is 100% copy case, right? So these two are the basic cases for now. This is the percentage similarity. This is the particular formula which we're using right now. And based on that particular result, this we have divided it, and low, medium, high result will be displayed. Clean white spaces, this was quite essential to use because while coding, one of the issues what we faced, it was like initially it was just taking the input of a single sentence and rest of the data wasn't getting printed, but later on we were able to overcome it with the help of this particular function. And the process text, actual assignment creation, how the entire content is going to the root and how root is actually building the entire assignment hierarchical tree structure. And this is a main function wherein we are initializing the child nodes initially with null, and then we are calling those particular values, we are processing text, and then we are comparing it. This is our terminal result. As you can see, initially we are printing the number of sentences in each assignment, and then we are comparing it line by line, and then you can see the overall sentence similarity being detected, and based on that particular condition, we have detected like it's a high score over here. And okay, this is our uh, particular score, like it's 12. I think it is not seen right now. Just a second. Yeah. This is a particular score which we could see on Turnitin. And thank you, everyone.
Thank you, everyone.
So the first question is, what's the time complexity of your comparison algorithm?
Okay, so the current time complexity is big O, where S, that is S into W square, where S is the sentences and W is the average words per sentence. This could also be optimized to big O, S into W using hash sets for word lookup.
And when I was seeing your code attentively, what made you use string token?
So basically, one of the major issues which we faced was when we were inputting the data to the particular function, it was only accepting a single line and it wasn't doing the same thing for the rest of the data. So later on, we came to know like this particular pointer, it was getting overwritten. So what we did instead, we used this different kind of pointer because it used separate pointers for each sentences, which helped us, like it didn't overwrite, and eventually it helped us to store a lot of data in the like sequential format. So that's the reason why we opted for this particular thing.
Okay, and what are the advantages of having both sentence and word nodes in the same tree?
Okay, so the core advantage of including both sentence nodes and word nodes in the tree is achieving dual level structural comparison. The higher level sentence nodes establish the document's flow and are used for macro level comparison of order and count. The lower level word nodes are crucial for micro level analysis by comparing the set of words under a sentence node. The system can detect if two sentences use the same vocabulary but are rephrased, that is, word in a different order. This deep structural check allows the system to flag similar sentences that are exact match checkers would miss, resulting in a more accurate plagiarism score.
And I'm very curious, why did you use trees and not any like linked list or any other data structure?
So it's quite easy to visualize because when talking about linked list, it's like a straight level. It's like a flat level wherein you move from one block to another block. So like there is no sequential level wise wherein you're in the main part, then you enter into the sub part as such. Whereas in case of trees, whereas in case of a hierarchical structure, what you can do is you can access the main part and uska sub part is the rest of the content which it is enclosing. And moreover, what I saw was like what we could have done is if we were using linked list in some or the other case, I think we would have completed this particular thing. But my particular like hierarchical structure, it is already considering the case where we are having insertion and deletion randomly. So basically, when talking about linked list, the main thing which comes in your mind is it's easy for like insertion and deletion processes. But in my current code, we have a particular function wherein the provided content, whether you make any small changes, like it is getting tokenized in the same way. So it doesn't matter whether you're inserting or deleting anything. So like that particular case is already being considered or covered in this particular part of with the help of this particular function. So we were able to do the entire thing better this way. So that's the reason we opted for trees.
Okay, and how do you determine if the plagiarism is low, medium, or high?
Okay, so according to the common academic thresholds, if it is below 40%, it is considered low. If it's between 40 to 70 to 75%, it is considered as a medium. And if it's above 70%, it is considered as high. If like we when we had given the demo, it was considered high since we got, I think, 70 to 75% plagiarism.
All right.
And like when we were doing the code, we faced many challenges. So I just want to know what was the most challenging part to implement from your point of view.
Initially, the structure, like the tree structure creation, obviously, because it was not just like a simple binary tree or like a BST, but it was kind like quite different. You had various sectors included within this particular thing, and integrating all those functions, that was another difficult part. And as mentioned earlier, like the tokenizing thing, that was the main issue we faced overall. Different functions, they work like quite well, but the main issue was while we integrated these two things, it wasn't working. It was only showing the output for a single sentence. The comparison was shown only for a single sentence among those two assignments. So yeah, as mentioned above, with the help of the different version of the string token thing, we were able to overcome that, and that's it. Then we were like good to go with the rest of the part.
Yeah,
That's
so basically the integration was a little difficult part to
Yeah.
overcome. But then, yeah, we did that quite
I think
easily.
from our side the questions.
Okay, great job, Aarushi and Molaika.
Okay, so guys, the first question is, what is the main objective of your smart traffic control system?
So the main objective is to manage vehicles efficiently at busy intersections, like by giving them priority to emergency vehicles such as ambulances or fire trucks, and we use a priority queue for this, while normal vehicles are handled in a regular queue. This ensures that there's minimal delay and the services are given properly.
Okay. So how are you all like implementing the priority thing for the normal vehicle and for the emergency ones? Like, what's the main thing?
So basically, we are using implementing in this logic, like if like the empty priority queue. So suppose the queue has some priority vehicle, like an ambulance or a fire truck. We'll make sure that it is prioritized first and we'll let go through it. But if that queue doesn't have any priority, if all the vehicles are regular, then we will act like it is a normal vehicle stand or a normal traffic only, and we won't let them pass through it. So the emergency vehicles are always passed first. Only when the priority queue is empty does a regular vehicle move.
Okay, fine.
Okay, so how does your program simulates real world traffic behavior? So, like, how is it relatable to the real world?
So it will basically tell us about the arrival of the regular and the emergency vehicles, and the automatic priority will be given to the emergency vehicles, and the other vehicles will follow continuous flow and visualize the traffic.
Okay.
Okay, so like, can your particular queue, like, how is the functioning? Is it linear or is it following a circular queue type of function?
It is not following any circular queue. It is implementing a linear queue where the rear stops at max -1. But if we want to make it circular, we can use rear equal to rear plus 1 and just the remainder to the max, and similar adjust it for the front value.
Yes, okay.
Oh, nice. So, next question is that how would you detect traffic congestion using your system?
So in the code we have uh, written max 50, but if it exceeds the threshold, like say 80%, then the queue, like then if the rear and the front is more than the 80%, then it will detect congestion, and this warning can trigger an alert or extend green signal during real world systems. So it just detects it.
Okay, so how does your system automatically detect the emergency vehicles? Like, have you all thought about it with that
Yeah.
aspect?
So in real world scenarios, emergency vehicles may be detected using sensors, RFID tags, or camera-based AI detection. So sensors can pick up the sound of the siren or the vehicle signals. RFID tag allows the system to identify an emergency vehicle as it approaches, and the AI cameras, they can recognize the flashing lights or the emergency markings. And the user will immediately get the manual input of the vehicle type, and this is how they'll be placed in the correct queue.
Nice, very good.
Okay. Yeah, I think that's it from our side.
Yeah.
Okay.
It
Thank
was a
you.
good project, according to us.
Thank you.
Thank you.